Assalamualaikum and good day. We meet again and we continue with our discussion regarding assembly language. We are continuing with the single register data transfer. As we know that the basic load and store instruction uh, is as shown here. Okay? LDR, LCR, LDRP, STRP. These are the basic load and store instruction. Where our version 4 also add support of half and sign data. Okay, some of it we are not discussing in here in our scope. Since uh, assembly language that we learn and architecture of the ARM processor is for a theoretical understanding. You are going to use a high level language in order to put during lab. So some of it which I'm not discussing in here means that we are not discussed. Okay, as we know that uh, the instruction, even the load and store instruction, also can be conditionally executed by inserting the appropriate condition code after STR or LDR. As we know, most of the uh, almost all of the instruction can be conditionally executed. Means that either you want to execute it or not. Okay, and it depends on the condition. Okay, this is the example. LDR and then the equation. So the syntax for the single register data transfer is load or store. Load means that you load it from memory. Store means that you store to memory. Then we have condition, then we have size, and then we have a destination and with the address. We are going to look into it later on. Okay, load and store word or byte which indexing this register. If we look here, in the memory location to be accessed is held in the base register. Okay, so the syntax, the code to use for RO, and then we have a bracket one where we store the content of RO. Okay, store means that we put to the memory. Okay, store whatever content in the RO to location pointed by content of R1. Okay, R1 in bracket means that it is an address. Address where you want to store. In full by R1. And then for load, we have load R2, R1. In this example, load R2, R2, whatever content is shown by pointed by the R1. So in load, so what was do we look at R1, what is the content of R1? That content actually the address. Go to that address and whatever value that you in the memory of that address, you go and put into the R2. So this is the destination R2. Okay, and the first one, let's say the address of, sorry, the content of register 1 is 200. So it will go to 200 and then store whatever content in R0 to this address. This is for the store instruction. And then we can have the offset from the base register. As well as assessing the actual location contained in the base register. This instruction also can assess the location offset of the base register content. You have base register, the content of register, then you can have offset by the constant value. Okay, where this offset can be an unsigned 12-bit immediate value. 12-bit immediate value, unsigned, means that from 0 to 4095 bytes. Okay, this offset also can be a register. You can make the offset as a register, optionally shifted by immediate value. Okay, this can be either added or subtract from the base register. So the offset either you can increase or you decrease from the offset value or register. Okay, this offset can be applied before the transfer is made. Then we call it as a pre-index addressing. Okay, we use it before the transfer is made, then we call it pre-index. Optionally, auto increment of the database register by postfixing the instruction with the what we call this notation. Uh, not sure what we call it. After the transfer is made, okay, if the offset applied after the transfer is made, then we call it as post-index addressing, where it caused the base register to be auto-incremented. Auto-incremented. See the example. Load and store index addressing, okay, where we have store 0, R1 with constant, okay, offset with constant 12. Does it refer to a base 10 12? Okay, we have R1, content of R1 is 200. And then we have offset. If we calculate from 200 offset to increment by 12, we get 200C. Okay, if the source register, since it is stored, means the input into a memory. If a source register is the content of source register is 5 hex. So to store to location 1F F4, instead use the R0, R1, the offset is negative 12. Immediate number negative 12. So negative 12 is actually decrement by 12 from 200. To auto increment base pointer to 200C, then you need to store R0, R1 12, and then you put this mark. Bahasa what we call kata seruan. Then after you execute the instruction, R0, R1 will contain 200C. If let's say the R2 contain 3, access 0 to 200C by multiplying this by 4. Okay? If the content of R2 is 3, if you multiply by 4, it becomes 12. If you access the same location. So what you can do, the other way to write the code is store R0, R1, R2, and then you shift by shift left by 2. So you know that if you shift left by 2, means that you multiply by 2 power of n, where n is 2, 2 power of 2 is 4. So R2 will multiply by 4. Load and store with or by post index addressing. Okay, this is a post index addressing. So if you have this example, store R0, R1 in bracket, and then you have immediate number 12. So if you look, the original base register is 200. Okay, after and the offset is 12. Okay, after you execute the instruction, it will be updated to 200C, and you store whatever content of R0 into this location, into the original base location. But after you execute the instruction, R1 will be 200C. This is what we mean by post index addressing. Means that you unload to original, but at the end of it, you are going to increment the base register. Okay, same as uh, if you are going to increment the base register to a location 1F4. Okay, then you can use R1 is the only inside the bracket, while the immediate, the constant value is outside. It meant that it needed by after you execute the instruction, R1 will contain 1F4. But the value that we store is at 200 at the original location, original pointed by R1. If let's say R2 contain G, then you can make auto increment this to R200C by multiplying this by 4. So it is same as the previous one, the only is a post index addressing. Means that It will only update and the R1, it will store it at original before it update. You see. Okay, load and store with user mode privilege. User mode, when using the post index addressing, there is a further form of load and store. Okay, actually, we are not discussing this part. Okay, this is and the other when we use a privilege mode, and we are not covered in our school. Okay, example usage of addressing mode. Okay, if you imagine that you have an array, the first element of which is to point by the content of R0. Okay, this is R0 pointed to the start of the array. Okay, this is the memory offset. Okay, this is the element that you are going to either to load or store. Okay. If we want to access a particular element, then we can use a pre-index addressing. Pre-index addressing means that it will implement and then get the value. So load the value, store or load. Okay, let's say R1 is the element that we want. Okay, R1 is the element that we want. So means that here R0 is pointing at the start. R1 not sure this is the element here. So you can load R2 means the input inside the R2. The original, and then you have the offset R1 we multiply by 4. And then R0 will be updated. R0 plus R0 give R1 multiplied by 4. Then you load to the R2. Okay. If you want to step through every element of the array, for instance, to produce a sum of elements in the array, then we can use post index addressing within a loop. Okay. Why we put LSL 2? We know each location is a byte. So in order to get all the 4 byte 32 bit, then we need to add 4. Okay, each of the location we need to multiply by 4. Okay, if you look here, the memory offset, this is the first memory, and the second one is to come in, and then 12, and so on. You just imagine that each is ARM processor is a 32-bit processor, means that the data bus is 32. So you can fill up the data bus with 32 bit. But memory only the space, the length of the memory is only 8 bit. So in order to full the 32 bit, you require 4 8 bit, 4 byte. Okay, so that's each of the 32 bit required for location. Okay, if you want to step through every element, okay, for instance, to find the sum of the element, then we can use the post index addressing within a loop. Okay, do the loop. Okay, for example, we use R1 is the address of the current element, initially equal to R0, and then you multiply by 4. You load first and then you update R1. Not multiply by 4, sorry, you add to 4. Use a further register to store the address of the final element so the loop can be correctly implemented. The offset of the half word and sign half word by access. Okay, the load and store. Okay, some part of it I'm not going to discuss this. Okay, and DNS also I think this is going to be in the our school since we have I think if you be in 226 course we have already discussed what we mean by DNS. Okay, so we just go through quite fast. Can set up to access the data. You know the engineers mean how you arrange the data. Okay. Which one is going to be first, which one is going to be last. The ARM can set up to access its data in either little or big endian. Little endian means that the least significant byte of a word is stored in bit 0 until bit 7. Least significant byte. But in big endian, the least significant byte of a word is stored at bit 24 until bit 31. So it is the other way around. And actually, ARM support both of it. Okay, it can use little endian or big endian. Okay, this has no real relevance unless the data is stored as word. Okay, when you use a data that stored as word, then access is smaller size quantity, either you want to access half word or byte, then it will give some effect. Because you want to know which byte or half word that you want to access. Okay, it depends on what kind of engineers that been involved in the system. Okay,